All right, good afternoon by 27 seconds. We're going to be talking today about moving to atomic system containers. Looking at one first, what is a system container? Why would you build one? What does it look like? And then what the Project Atomic team has been working on to make that even better. My name is Matt Micene. I'm an evangelist with Red Hat, and with me today.
I am Giuseppe Scrivano, and I work on Project Atomic, and more specifically on atomic system containers.
All right. So let's do a quick container review. Show of hands. How many people know what a container is? Yes, 100%. Good. So why would I go over what basics are of say, an image? So one of the reasons I want to make sure we talk about this is simply because there are changes at each of these layers that we will be talking about as we talk about system containers, and some of the things you want to do slightly differently for each layer. So images, right, that's our layer of transportability. That's our distribution mechanism. So we're going to be treating the images slightly differently than you may say for a standard container, because we'll have things that want to install like a regular system service. So there will be things you want to interact with the host, and you want to make sure that when you build these sorts of containers, you take into account those sorts of interactions. And speaking of the container itself, right, once we have the runtime in motion, normally we see containers that capabilities get dropped. We want to make sure that they are fully isolated from the operating system and operating system components. But for system containers, that may not be the case, right? We actually probably need to have some sort of visibility into host file systems. We may need to have slightly greater control over network namespaces, right? So these sorts of containers are probably a little more privileged than your typical application container you might be used to. So we're looking at a class of container that we want to be able to do something similar to a system service on the actual host, right? And if you don't believe us, maybe you'll believe Kelsey Hightower as we talk about this. Just because you containerize something doesn't mean you have no responsibility to understand what the software in the container actually is going to do, not just as a service, but also to the system upon which it will run. So we need to know how these things work. We can't just randomly download things from the internet and run them, which is sort of the primary use case for a lot of these things in distribution. The first question around system containers versus what you may typically think of as a containerized application is whether or not you need orchestration. So the ideas behind standalone containers, which is the basis for what we'll be talking about, versus orchestrated, these are some of the arguments, right? We're talking about things that generally may have just a single container for the application. We're not talking about multiple different microservices that need to be containerized, that need their own sort of separation, and therefore we don't necessarily need a high degree of coordination between those containers. Failover is possible for a system container, but not a necessity of how it's built. There may be alternative ways of keeping state in sync. There may be alternate ways of doing failover and multi-master environments based on the application itself. And we're not going to need some sort of external service to watch and make sure that our application components are up and running. We probably only want one of these running per host, right? In some of our application containers, if we have multiple load-balanced web servers running on the same host, that's perfectly fine. But for some of our system services, if we start to take a look at, one of the things that the team is working on upstream is containerizing container runtimes. We're not going to want more than one CRI-O running on the same system. That would be bad, right? So we want to make sure that we only have one per host. The OpenStack folks upstream also have been working on a couple of different ways of containerizing their services that make up OpenStack. Again, one per host, otherwise we run into major issues. They also tend to interact with the host much more than an application container. An application container generally ignores the host, right? That's the purpose of that transportability, is we can run this anywhere once we've built it. We can still run system containers anywhere once we've built them, but they're generally designed for those things that want to have some sort of control or expose some sort of mechanism in the host. Again, we go back to, say, a container runtime where we're actually interacting with kernel processes in order to build containers. That is going to need a little more standalone capabilities. It's not necessarily a clear line. For example, etcd can, depending on use case, can fall into either one of these two categories. It has its own mechanism to synchronize and maintain cluster status. We could need one per host. We may not matter so much. And it really depends on, is this an external infrastructure service that's being used, or is it part of an application? So the simple line being drawn around an application really may not be enough of an indicator to say, oh, well, it's this process and therefore it shall do X. So why would we do these sorts of things? We'll take some simple, basic ideas here, right? So for a typical network environment, we generally have multiple simple services running that we usually wind up having to isolate in virtual machines. We isolate them for update reasons, right? We don't want changes to an operating system to break other services. We may have some network conflicts, but generally we're wasting a lot of resources and introducing a lot of overhead and management simply because we want DHCP and DNS to run on separate virtual machines in our networks, right? If, however, we could containerize those services, we get all of the benefits that we would get from a general container, right? We get the same sort of separation that we want from a process and capabilities standpoint, but we're now sharing resources. We're sharing and using the reducing management on the with a shared operating system. And we still have that flexibility that we need if we do have to share IP or constrain IP resources, CPU, RAM, disk, those sorts of things, right? So we get a lot of benefits for typical network services for single host applications. So let's pick on a particular simple service. We'll pick bind because, well, bind's fun. It's already designed for a CH root, which makes it particularly useful and easy to containerize, as you'll see in a second. It's generally got a fairly simple config structure, which makes it easy to talk about, unless, of course, you don't have a very simple config structure, which is very easy to do with bind if you need to run highly available, large-scale services. But for the most part, we can get away with talking about like one directory and like one file here. It needs network, but not a whole lot else, right? This kind of breaks some of the paradigms we were just talking about lots of host access, but this is an example. And it does use child processes, which means we're going to want to integrate this with systemd, which may be a bad word in some people's lexicon. But we want these things to start and stop like standard services. We don't want to introduce a new mechanism for process management, right? So we're starting some things with our init system, we're starting other things with one container runtime, we've got a third container runtime and a third way of confusing admins on how did this thing start on my system and how do I stop it and how do I restart it and how do I update it, right? So bind was a pretty easy way for us to start this project and just kind of give you something to look at. So we need a couple of things. Persistence to the host so we can manage it a little bit easier. We want to copy the zone files down to the host. We want to copy the configs, right? That way we can edit it like we would a normal bind service, but we've got it containerized. We need the CH root, boom, container, done. And we're going to integrate it with systemd for the reasons I already mentioned. So let's talk about how we would build one of these things by hand today without using an atomic system container. We'll set a little baseline first. So from Fedora 27, and I can't quite see these, so I've got some links. I've written about this for my day job using RHEL, and I've got a GitHub repo that has some examples here on how you would do this by hand. But essentially, for Fedora 27, what we would need is, we need some file system space, right? We need to be able to access etc. We need to be able to access var, right? We need to be able to create enough space to hold our bind files. And you need a text editor, whatever that is up to you. Text editor, entire new operating system called Emacs, whatever your preference is. We need Docker installed. right? We have to build the Dockerfile, we have to build the container in order to get what we're going to do, and we're going to need to run it eventually, and we'll talk about that. We need systemd in the base container. So that will influence your choice of which container you need to use. For example, Red Hat in Enterprise Linux distributes two different kinds of containers. There's one with and without. For Fedora 27, systemd is already available. And we'll just need to add a unit file so that we can control the service and the container through systemd. The Dockerfile for bind is very simple in this case. Right? Another reason we used it for this example. We simply install bind and bind needles, we clean up after ourselves, and we tell systemd in the container to go ahead and enable that service. Right? We'll use some OCI hooks and other things that'll need to be installed on the system in order to get that to systemd on the host to talk to systemd on the in the container. And the other things we'll need to do then is to tell it what we need to expose for ports, and then we tell it to use init as its run command, right? We're not telling it to run bind as the run command in the Dockerfile. I have a feeling there was something else I was going to say here, and I don't remember what it was, so we'll skip it. So this is a very manual process, right? We need to set up that Dockerfile. We need to build it. Once that container is running, we need to copy out files, either with Micene-CTL, Docker copy, however you feel like getting files out, so that you can do modifications, you can get those on the host system. You'll need to figure out, one, if it's a service you haven't seen before, you may need to interact with RPM and figure out, say, hey, what files do I actually need? Figure out mount points. With more configurations, this gets more and more complex. Bind, like I said, we picked it because you can do this with one config file and one full directory copy. If we've got something like IDM with multiple services, multiple configs, it gets much, much more difficult to use a more complicated process. Then the question then becomes, as we manage these things, how do we update it? It's perfectly fine to do this sort of donor container, pull things out, make myself a final container that has mount points and things. But that means we need to go through this every single time we need to update bind, which really puts a burden on us as we manage these things. And honestly, creating a good systemd unit file to start and stop something in Docker, there's like 47 competing ways on the internet of figuring out how to do that. So whether or not yours is good is kind of up in the air because there's all sorts of odd edge cases. So that's the manual process. It's fine, it works, but there's obvious problems. I'm going to turn it over to Giuseppe so that he can talk about atomic system containers and how we fix some of those problems.
So let's start introducing a bit the concept behind system container. An atomic system container is our way of running system services inside of a container using a set of already existing technologies. For example, we use Scopio for interacting with the registry and to pull the images. We use OS3 for the storage of the images. OS3 is the same technology used for Atomic to store the operating system images. And then we delegated directly to run C to run the container, and the life cycle of the service is managed through systemd, like any other service on the system. Now we will go quickly through these three phases: how to build one, how to run, and how to keep updated, and how a system container simplify the second and the third phase. I think they went out of order. Yeah. So the build is done in the same way like any other Docker image. We use exactly the same structure. We use a Dockerfile. The only difference is that to run a system container, we require additional metadata. And this metadata is distributed as part of the image itself. We did this so we don't need another source to copy this metadata for running the container, and also that it tracks the image as it's part of it. And a very interesting feature that we added recently is the possibility to copy files from inside the container to the host at installation time. We will see this more in details later. But basically, we have a special directory inside of the container image that it's read at installation time, and all the files present here are copied to the host, and we keep track of them. I was saying that there are additional files required for system containers, and here we have a list. The first one is the most important one, as it's the configuration for run C, and it specifies how the container runs. It specifies what privilege it has, what mount points, and well, the C groups and anything that it's required for running a container. The other three are optional, and they are you have the possibility to customize them if you are not happy with what Atomic generates by default. You can, if you are not happy with the service file for systemd, you can customize it with your own. But by default, it generates a systemd file that runs C and the container. Also, we offer the possibility to create temporary directory or files if the container requires them to be present before it runs. And we have a file for various settings. This is how a Dockerfile for a system container looks like. You can see that the first three lines are basically the same structure that we used before. We install the packages, and then the copy and the run directives are for managing the system container. The first one is to copy the configuration for running the container. This is a template file, so it means that Atomic install will process it to generate a final configuration for run C. It's OCI runtime. And in the last directive, we can see how this new feature looks like. We basically copy some files created by the bind inside the container to this special directory in the image, exports hostfs. So whatever is there when the container is installed is mapped in the same location on the host file system. So whatever it is named D will be copied to the host before the container runs. So you can simplify the configuration of services by having these files on the host, and this is done by the system containers without any manual intervention from the users. And this is how a system container is installed. The command actually is simpler than that. We don't need to specify system package. I just put it here to give an idea and of how this works. So here we say basically to install a system container. In this phase, the configuration file for run C is generated. A systemd service file is created, and all the files that are found in the image in the exports hostfs are copied to the host. As you can see, you will find them at the usual location on the host, like etc named D. Also, we have an Ansible module for installing system containers, so you don't need to do this like manually, but you can just use the Atomic container module, and this will the snippet we see there does exactly the same thing like the Atomic install command. It's exactly it pulled the image and installed it. Yeah, in this phase, the system is not running yet. So if you need, you have some time to the time to configure these files and customize them before you start the systemd service. We also have, if you see the difference, we have a system package yes here, differently from equals no before. We have this way of generating an RPM on the fly of these files that are copied to the host. We did this so that we don't lose ownership on the host of the files that are there. Because if we simply copy files to the host, then we cannot use tools like RPM to see from where this file is coming from. Having this additional step of generating an RPM from the rootfs in this export hostfs directory gives us the possibility to install an RPM like you would do like for any other package on the host. So you will be able to track ownership. And we also delegate to RPM the management of different versions. So if you modify your version and you update the container, this will not be overwritten because well, it's like any other service already present on the host. We also added a way to a bit abuse this mechanism by having this new directive in the manifest file, no container service. If you specify this option, the atomic install will not create a systemd service. So basically, only the files that are exported to the host will be copied there. It's, well, we don't really suggest people to start using it, but it's only useful if you already have a Docker registry in place and you want to use it also to copy any other kind of content to the host without requiring maybe a web server for RPM serving. And then you can just manage one single service for delivering content to the machines. As I was saying, the configuration files present for system containers are template files. We allow some basic customization at installation time. And the same mechanism is allowed for files that are copied to the host. So if you build your system container using this feature, you can allow, for example, to specify, to customize the file that is copied to the host. And so you can use a single command to copy the file and parse it, process it through the templating mechanism and copy it to the host. So in the bind case, for example, you can customize how the zones look like. And the good thing of doing this is that once these files are generated, they are tracked. So the generated file is tracked both by RPM if you install an RPM or Atomic if you just copy the file directly. So it means that if a new version comes, we check what files are modified, so we don't override your changes. And to keeping the container update, it's just a matter of pulling a new version of the image, and we use atomic pull -- storage OS3. That internally it uses Scoped to contact the registry, pull the updated image, and put it in the OS3 storage. And then we have atomic containers update. And in this phase, we check, is the image newer than the version we have installed? If yes, then we proceed with installation. We generate the files, and once the files are generated, we stop the service, the running service based on the previous version. We swap the files with a newer version, and we restart the new version. The nice thing of using OS3 is that we keep always for a system container 2 deployments. The previous version, that was the one you are upgrading from, and the newer version. So you are always able to go back to the previous deployment if something goes wrong during the update. And this is the same mechanism used on Atomic host, more or less, for the upgrades of the operating system. And OS3 manages the duplication of files via the links. So if two deployments have files in common, there is only one copy on the file system because it's deduplicated with hard links. So after the update, you have the possibility to go back to the previous deployment. That does through atomic containers rollback. That does exactly the opposite thing. It stops the container, the service of the new version, swaps back the old version of the files, and then restart it. And unless something really bad happened during the update, like destroyed the storage or something, it should be possible to go back to the previous version and have no problems running it. We realized that if people start using system containers, it's a bit problematic to keep track of all of them updated. So we provided also a way to update all of them with one single command. Well, two commands. One is to update all the images that are in the OS3 storage with atomic images OS3 storage OS3 update --all, and this fetches the newer version of all the images that are known locally. And the second one tries to update all the system containers sequentially. A difference between atomic containers update --all and the manual update of a single container is that it verifies if the service comes back. If the service fails to restart, then it automatically rolls back to the previous deployment. So, yeah, so you can fix it before causing some downtime, and then you can update it manually if there is any instance that is failing. And I will show you now how these things work. Yeah, this image is already on Docker Hub, so if you want to play with it, you can already try it. So we are telling Atomic to pull the image that is not present in our storage yet, and we just delegated this to Scopio, as you can, and that copies the image to the OS3 storage. Here we try to install the system container, and Atomic install --system, and here you can see that it creates some files on the host file system. All these files are generated, and we can see that the service in this moment it's stopped. It's installed, but it's not running yet. And there is, I'm not faking it. There is no other service listening on the bind port. So we can run the service like any other, as we are used to with systemd. And there is there is bind running. We can use the same tools to check the status. You see, it looks very familiar. Output, it doesn't go through another Docker. It's all entered through systemd. And here we try to the upgrade and how it looks like to update a system container. We pull a new image, only the layers that are, well, this is done by Flescopied, but only the layers that are changed are pulled into the OS3. And once the new image is present, we try to update the container to the new version. And from the output, you can see that internally Atomic stopped the service, it removed the temporary files that were used before, copied the new files, and this is done because we didn't modify any of them. So it's so from the previous deployment they were coming. The version present on the host is the same version coming directly from the image without any customization. If in this phase Atomic will find some mismatch, like that the file is modified, it will leave the version that the user created. And we see that the service is running again after the update is complete. This is how internal is done. We create two deployments, bind.0 and bind.1. Each of these has the complete checkout of the image. Bind.0 is the previous version that we were running. Bind.1 is the newer one that we just updated to. And then we have a symlink bind that points to the current deployment. Yeah, we can see that it points to bind.1, that it's the newer version. And this, assuming something went wrong and we want the previous version back, we use rollback. And we see that the deployment now changed to the previous version. And the container is still running.
What technology do you use to run the container?
So the question is what technology we use for running the container in the system. We use runc. Runc, well, we use any OCI runtime. We can use any OCI runtime, but for now we are using runc. That it's the core technology also used for Docker containers for running the actual container. It's you provide it configuration files specifying how the container should look like, and it takes care of creating the process. Yeah. So no, we don't require Docker. We don't require any other daemon except systemd for managing the service. Okay, this one. And here I want to talk a bit of other few features that we added recently to system containers, and that I think it's interesting to know about. We support running OpenShift using system containers since 3.7. These are the configuration you need, the Ansible configuration you need for doing that. If you specify OpenShift use system containers in your inventory file, you are able to use system containers for the OpenSwitch master and kubelet system containers. We also have a system container for running CRI-O, and we run even Docker in a system container. It's possible to do that. We also added that. Well, before system containers always needed to use systemd, but we found that there were cases where we don't want that. We just want to be able to run a container even early in the boot that doesn't require any other service. For example, for the OpenShift installer, we would like to be able to run the installer, but at the same time we can't run this inside of a Docker container because the installer of OpenShift configures Docker. So we are running a container inside of Docker and at the same time configuring it. And it's a chicken and egg problem because we can trigger a restart of Docker that kills the container. So we wanted to be able still to use the system container mechanism for this. And for doing this, we added a label, atomic run, that if you set it to once, atomic install will not try to install the service and any other file. It will just run the container like interactively, and you will get the output directly to where you are calling the process without going through a service. We also changed the way we label the files inside of a system container. We use the same, for a files inside of a system container, we use the same label that a file would have if it was installed directly to the host. This gives the possibility of using different kind of policies for services running inside of a system container. If you run containers using Docker, you will get that all the processes have the same label, and this This is a big difference when you compare two services that are not running inside of containers. We want to be able to do that. We want to specify different policies for different services. And also another advantage of doing this is that we finally can share the same storage with OS3 on Atomic when using the same when using OS3 also for managing the operating system images. Before we had the problem that files coming from a container had a different SELinux label, and the way that OS3 works is that it calculates a checksum of the entire file, including also the extended attributes. So if the file was already present in the atomic host operating system, we would still create another copy because there was a mismatch just in the SELinux label. So now this is also solved by using the same label. The biggest problem we had using, for Container-ized CRI-O and Docker is that we want to give the process a bigger control of the host, and not what you usually think with container, that you want to restrict what they operate on. So really now the only requirement for running a container is to have a new mount namespace. Everything else can be shared with a host. This is not much done in Atomic install, except for giving some, to facilitate this task when writing a configuration file for RunC. Also, we are looking into using all we have now for running containers like a non-root user. So it works in the same way, except that we use a different OS3 storage for each user, so it's not shared with a system. The service is managed via via the user instance of systemd and not the system instance. There is no support in this case for copying files to the host because you don't have the privileges for doing that. The biggest difficulty I've seen is that the configuration file for running the container must specify a user namespace. And the time we started to work on this, the RunC didn't allow to run containers as a non-root user. So we brought a minimal OCI runtime that it's bubble wrap OCI. It's basically converted the OCI configuration file to a command line for bubble wrap. Bubble wrap is the same technology used by Flatpak for running containers as a non-root user. And that's it. Any question?
Jag?
Yeah.
Thank you. Awesome presentation. Have you guys considered, so you're doing all of your installation and managing this through the Atomic utility for old people like me who are really used to using RPM. Have you guys thought about taking these containers and bundling them up in an RPM so that I get my systemd controls, I get my etc configuration, but the image layers are just in bars that wherever RunC likes to store those, so that I can update them using RPM set.
So the question was, so that they can hear it on the broadcast, this is all great. It all uses the Atomic command line in order to do install, update. Have we looked at using a more traditional, old school methodology for distributing and installing these things that wraps that, like just bundle the whole thing in an RPM that also then has some mechanism to do all of the things that the Atomic command line would do while maintaining an alternate distribution format. Fair?
Yeah, so there is a hidden feature in Atomic that I didn't talk about because I'm still not very happy about it. But basically, when you specify system package, you can also yes, no, and there is also another mode that's build. It builds an RPM containing the entire content of the container and also the files that are copied to the host. So you can install the RPM containing all the files that copy to the host plus the files under varlib storage for running the container.
But if I'm like, say, managing 1,000 systems using satellite, I need that RPM to go into some kind of feed, right? I can't just take my own RPM and just throw it in.
Yeah.
So the
Yeah,
question,
you will still. Okay.
so the question was, the follow-up was, what about managing that at scale and having to manage that RPM in a repo?
Yeah, you will need a way to distribute that RPM and in some other way. Yeah.
So there's definitely work to be done.
Recently, I didn't even know about this technology, but I was thinking of a way to distributing images in RPM. And I want to do this in Copper build system. So perhaps I think I will get like more familiar with this technology, and I will try to make it work. So
And apparently someone in the audience wants to make that work, so pull request, welcome. Vincent.
So, in the beginning, you said you have to install Docker to build from a Dockerfile. Is that the only way to build from a Dockerfile?
No.
So the question was, in the beginning, we said, do you have to yum install Docker for a Dockerfile? Is that the only way to build? So first, the one thing I do want to make sure we know that the first half, my part of the presentation, was things not to do. Well, it's how you would have to do it today without access to technology like atomic system containers. And the SELinux thing, by the way, that was the thing that I blanked on, that I said, oh wait, I forgot to say something. The SELinux context, if you do it that way, is it all has to be whatever your container runtime is. So it's not necessarily the only way to do it. It's just that you could do it with any of the standard Docker, any of the standard ways you would build a container of that nature. It just so happened that I was using Docker and Docker build to do that. So no, you don't have to do it that way, but please don't use our new stuff. So yeah, I could probably go back to the original named container example and do that with Builda. I saw other hands. Yes.
I was just going to comment on the RPM redistribution. For managing at scale, I have actual Ansible jobs. With the updates, having the Ansible module deploy updates just makes it easier rather than just doing updates.
Yeah, so the comment, if I characterize it correctly, was for management at scale, using and having the atomic container module for Ansible would also help, especially if it did some of the management of updates and as well as installs, which...
Yeah, I forgot to mention that also during the update you can use the Ansible module. If you use the same snippet that we saw for the installing the container, it will try to upgrade the service to the latest version. And if the version didn't change, you will get the idempotent not changed thing in Ansible.
Steven?
So I had a couple of questions. One was, do you have SELinux support? I was really keen to see that. Thank you so much. I would like to know, are you building the SELinux label at build time or install time? Because there's a compatibility issue there. If you have different host store times with different SELinux policies, portability is an issue there. And the second question is, can I also lay down additional UIDs for services that come with run as drop my remove, run as Apache remove my remove?
Okay, so we'll remember your second question because I will forget it by the time I repeat this and have Giuseppe answer that. So the first question was about SELinux policies, and the comment opening was, thank you for supporting SELinux. But the question was, when in the process does the SELinux policy get built? Is it during build time or is it during install time, and how does that work with potential mismatches between build environments and runtime environments and policy as you go from the distribution model to the actual install and run?
So we actually don't have the way to install a new policy. We use the policy that is already on the host for labeling, for relabeling the files in the container. So
Do you do that when you build it or when you install?
when you install it, yeah, when we install it, we change the label for each file. Yeah.
Okay. And the second one, I told you. I
Do
forwarded.
you also support adding UIDs on the host and mapping those in?
And
So do we also support mapping UIDs, or for services that deliver and expect particular UIDs, do we have a mechanism for pulling that out of the service and getting that user on the runtime host?
no, we don't actually do that. We expect to run like root the container. Yeah, you could. Well, I didn't try that, but you can specify the UID inside the OCI configuration file. But then you need to be sure somehow that this ID is present on the host. And yeah, we didn't get to there yet.
So there's some work to do there. Pull request button. All right. So we talked a little fast, so we're ahead of schedule. Any other questions from this side of the room, since this has been a very quiet side of the room? No? Everyone gets it? We got it? Steve? Yes? Oh, that's thumbs up? Okay. Sorry. Wasn't a question. All right. Well, if there's no further questions, hopefully this was useful. Hopefully we got our point across. So feel free to ask us questions later.
Thank you.